Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, New Horizons map, hidden hydrogen cloud near Earth and black hole dissonance mystery. New Horizons unveils first Lyman-Alpha map of the galaxy. NASA's New Horizons spacecraft has achieved a major milestone by creating the first ever map of the galaxy in the important ultraviolet wavelength known as Lyman-Alpha emissions. This new view offers a fresh perspective on the galactic regions surrounding our solar system. The findings have been detailed in a study led by the Southwest Research Institute, SWRI, and published in the Astronomical Journal under the title The Lyman-Alpha Sky as Observed by New Horizons at 57 Astronomical Units, authored by Dr. R.G. Gladstone and his team. The study explains that understanding the background of Lyman-Alpha emissions helps scientists better grasp the structures and processes occurring near our solar system. The research points to the idea that hot bubbles of interstellar gas, such as the one in which our solar system resides, may actually be regions where hydrogen gas emissions are enhanced at the Lyman-Alpha wavelength. Lyman-Alpha refers to a particular wavelength of ultraviolet light that is both emitted and scattered by hydrogen atoms. It is especially valuable to astronomers because it aids in studying distant stars, galaxies, and the interstellar medium by providing clues about their composition, temperature, and motion. While New Horizons was on its primary mission to Pluto, it began collecting baseline data on Lyman-Alpha emissions using an ultraviolet spectrograph instrument called ALICE, developed by SWRI. A spectrograph is a device used by astronomers to break light into its different colors, allowing detailed analysis, and ALICE specializes in the far ultraviolet part of the light spectrum. After completing its main mission at Pluto, New Horizons continued its journey deeper into space. Scientists took this opportunity to conduct broader and more frequent surveys of Lyman-Alpha emissions using ALICE, including a significant set of scans in 2023 that covered about 83% of the sky. To focus solely on emissions from outside the solar system, the New Horizons team created a model of scattered solar Lyman-Alpha emissions and then subtracted these from their data. What remained revealed a surprisingly bright and fairly uniform Lyman-Alpha background, about 10 times stronger than what earlier estimates had predicted. The results indicate that the emission and scattering of Lyman-Alpha photons likely come from hydrogen atoms within the shell of a hot interstellar bubble surrounding our solar system and nearby stars, a structure believed to have been formed by supernova explosions a few million years ago. Interestingly, the study found no signs that the so-called hydrogen wall, a theorized accumulation of interstellar hydrogen atoms at the edge of the heliosphere, significantly contributes to the Lyman-Alpha signal. Scientists had previously suggested that such a wall would form as the solar wind encountered the interstellar medium, but New Horizons data provided no evidence to support this idea. The research represents a landmark achievement, providing the first clear and detailed look at the ultraviolet sky around the solar system. It not only uncovers new characteristics of our galactic environment but also challenges older theories that are not supported by the New Horizons observations. This new Lyman-Alpha map now lays a strong foundation for future studies aimed at further uncovering the mysteries of the space beyond our solar neighborhood. EOS, a hidden giant hydrogen cloud near Earth. An international team of scientists led by a Rutgers University, New Brunswick astrophysicist has made a remarkable discovery by identifying a potentially star-forming cloud, one of the largest single structures in the sky and among the closest ever detected to the Sun and Earth. This enormous ball of hydrogen, previously invisible to researchers, was found by targeting its primary component, molecular hydrogen. For the first time, a molecular cloud was detected using light emitted in the far ultraviolet part of the electromagnetic spectrum, an achievement that paves the way for further exploration using this method. The scientists named the newly found molecular hydrogen cloud Eos, after the Greek goddess who personifies dawn. Their discovery is detailed in a study published in Nature Astronomy. Molecular clouds are regions composed of gas and dust, with molecular hydrogen being the most abundant element, serving as the essential building block of stars, planets, and ultimately life itself. These clouds also contain molecules like carbon monoxide, which has traditionally been used to detect such clouds through radio and infrared observations due to its strong chemical signature. However, in this case, the researchers took a different approach by looking directly for molecular hydrogen emissions in the far ultraviolet range. The data revealed glowing hydrogen molecules detected through a process called fluorescence, making the cloud visible in a way that had never been achieved before. This method allowed the team to observe Eos literally glowing against the darkness of space. Despite its proximity, Eos poses no threat to Earth or the solar system. Its closeness instead offers a unique opportunity to study a major structure within the interstellar medium, the material that fills the space between stars within a galaxy and acts as the raw material for new star formation. Observing Eos gives scientists the chance to better understand the processes of how molecular clouds form, dissociate, and eventually lead to the birth of stars and planetary systems. The gas cloud itself is crescent-shaped and located about 300 light-years away from Earth, sitting on the edge of the local bubble, a vast cavity filled with hot gas that surrounds the solar system. In terms of size, Eos stretches across a space in the sky equivalent to about 40 full moons and contains a mass roughly 3,400 times that of the Sun. Using modeling, scientists estimate that the cloud will evaporate in about 6 million years. The innovative use of far ultraviolet fluorescence emission techniques, as demonstrated by this discovery, could dramatically transform the understanding of the interstellar medium. It could allow hidden molecular clouds to be uncovered across the galaxy and possibly even at the furthest reaches detectable from cosmic dawn, the early period of the universe. Eos was revealed through data collected by a far ultraviolet spectrograph called FIMS-SPIR, an instrument on board the Korean satellite STS-AT-1. A far ultraviolet spectrograph functions similarly to a prism but for ultraviolet light, breaking it into its component wavelengths and producing a spectrum that scientists can analyze. The data set used for this discovery had only recently been made publicly available in 2023 when it caught the attention of the lead researcher. The identification of Eos highlights the importance of new observational strategies in expanding the understanding of the universe. Unlike traditional molecular clouds heavily traced by carbon monoxide, Eos is largely CO dark, meaning it contains very little carbon monoxide and therefore does not emit the standard signals picked up by conventional observation methods. This quality explains why such a massive structure remained hidden for so long despite being relatively close by cosmic standards. The hydrogen within the Eos cloud dates back to the time of the Big Bang, about 13.6 billion years ago, and over cosmic timescales, this hydrogen gradually made its way into the Milky Way, eventually assembling near the Sun, making the discovery a reflection of an incredible journey across the universe. The detection of Eos came as a surprise to many scientists, challenging long-held beliefs that molecular hydrogen could not be easily observed directly. It is particularly remarkable that the cloud was found in data sets that initially were not expected to reveal such structures. The name Eos also ties into a proposed NASA mission that some of the researchers are supporting, aimed at extending the search for molecular hydrogen clouds on a much larger galactic scale and further investigating the origins of stars by studying the evolution of these clouds. Beyond Eos, the team continues to explore data for both nearby and distant molecular hydrogen clouds. In fact, a study recently submitted to arcs4.org reports that using the James Webb Space Telescope, researchers may have tentatively detected the most distant molecular gas ever observed. In this way, the team has managed to uncover both some of the nearest and furthest molecular hydrogen structures using far ultraviolet emissions, demonstrating the enormous potential of this groundbreaking approach to reshape the understanding of star formation and the molecular universe. Black hole dissonance mystery solved. A long-standing mystery in the study of gravitational waves from black holes has finally been solved by a scientist at Tokyo Metropolitan University. This problem, which had puzzled physicists for nearly 3 decades, involved a strange dissonance observed in the gravitational signals emitted by black holes, an unexpected irregularity in the way these immense cosmic objects vibrate. Black holes, regions of space so dense that not even light can escape their gravity, have only recently become observable through the ripples they create in spacetime, thanks to the development of gravitational wave detectors like LIGO, Virgo, and CAGRA. These global collaborations have opened an entirely new way of studying the universe, allowing scientists to detect the aftermath of cataclysmic events like black hole mergers. Gravitational waves, much like the sound produced by a ringing bell, consist of a series of distinct frequencies known as modes. Each mode corresponds to a different way the black hole oscillates or rings after a merger. In theory, these modes should behave in an orderly and predictable way. However, in 1997, a graduate student named Hisashi Anazawa from the Tokyo Institute of Technology performed calculations that revealed a peculiar anomaly. One of the modes appeared to act out of step with the others, creating a kind of mathematical dissonance. This finding was so strange that many assumed it must have been a computational error or some quirk of the methods used. But even with the advance of computing technology, the anomaly stubbornly persisted and remained unexplained. Now, Associate Professor Hayato Motohashi has finally unraveled the mystery. By applying extremely precise computational techniques and drawing on a new branch of theoretical physics called non-Hermitian physics, he discovered that the unusual behavior did not arise from a single rogue mode, but from the interaction between 2 distinct modes. These 2 modes were resonating with each other, essentially amplifying or distorting each other's effects in a way that produced the previously unexplained dissonance. What's more, this type of resonance isn't a rare fluke. When Motohashi expanded his analysis, he found that such resonances appear widely across many different black hole vibration modes, suggesting a universal phenomenon. The implications of this discovery stretch beyond astrophysics. The resonance effect observed in gravitational waves has parallels in other areas of physics, including optical systems where electromagnetic waves exhibit similar behavior. This connection has led to the emergence of a new interdisciplinary field, non-Hermitian gravitational physics. By incorporating this new framework, scientists can better interpret the data gathered from large-scale observatories like LIGO, Virgo, and CAGRA. This breakthrough not only resolves a decades-old theoretical issue but also equips physicists with a deeper understanding of how black holes behave and how the fundamental forces of nature operate under extreme conditions. It marks a significant step forward in black hole spectroscopy, the study of these objects through the gravitational nodes they emit, and offers exciting new directions for research across multiple domains of physics.